Hello everyone, today we are going to understand what is sliding window technique. It is one of the most important DSA question patterns for interview questions, which makes it essential to have it in your arsenal whenever you are trying to give a coding interview. The reason sliding window technique is asked a lot in coding interviews is because it actually makes this order of n square solution into an order of n. Isn't that amazing? You can take the order of n square time complexity solution and convert that into an order of n time complexity. It is a huge improvement in time complexity. And that is why the sliding window technique is asked so much in the interview question. Now, before we go ahead and understand sliding window, I am assuming that you know some basic stuff like for loops. You know about them. You know about big O notation. What is n square? What is order of n? This is like the basic stuff that you must know before we proceed to understand the sliding window technique. And if you do not know these things, then I highly suggest you that you understand them before you try to understand the sliding window technique. At least understand the for loops and the basics of the programming, because there is no point in trying to understand something like sliding window when you don't even have your own basics ready. So the first question is, what exactly is a sliding window technique? Sliding window is a technique in DSA that helps us to solve problems that involve contiguous ranges of elements, which means subarrays or substrings, and not just the individual pairs. So what this means is that we need to use a sliding window technique when we are dealing with contiguous range of elements. Contiguous means adjacent. So suppose that we have an array like this. We have elements like suppose 1, 2, 3, 4, 5. Okay. And we need to get some contiguous elements. So one set of contiguous elements is right here, 2 and 3, right? But another set is also right here, 3, 4 and 5. It is also a contiguous set because all of them are together. 3, 4 and 5 are adjacent to each other. 2 and 3 are also adjacent to each other. That's why they are contiguous. So it means it's a very specific situation. Sliding window will only work when we have contiguous elements that are adjacent to each other. And that is why we have this specific cases, subarrays and substring. Right now, this 3, 4 and 5, this set is what? It is a sub-array, right? It's a subarray. And that is why we can think of using sliding window on arrays. Similarly, we can have strings like A, B, C, D, E, right? And then here we have substrings. This is a substring, right? It is a substring. Then this B and C is also a substring. Why? Because all these elements are adjacent to each other. And so understand guys that this sliding window technique will not work on subsequence. It will simply not work. Why? Because the subsequence is like this. We have elements in the array and the subsequence is basically a range of element, but those element does not have to be contiguous, right? So I can take 1 and 3 from here and this is a subsequence. So I can take from here 1 and 3 and this is a subsequence. It is not a subarray. It is not a contiguous sequence. Why? Because 2 is right between 1 and 3 and we did not take 2. So it is not a subarray, and the sliding window only works when we have contiguous elements. So it means if we have 1, 2, 3, then it will work. But when we only have discrete elements like 1, 3, it will not work because we need contiguous elements. Now, if you are getting the question in your head that why only contiguous elements? Why not just any subsequence? And the answer is very simple. Sliding window was designed for a particular purpose. It was not designed for subsequences. So subsequence were not a customer for this technique basically. It was only designed for a specific use case, and so it does not have a way to deal with subsequences. And as the word itself says, it's a technique. It is not an algorithm, right? A technique is something that you use in specific situation to deal with the specific problems. And subsequence actually have a different problem than contiguous subarrays or substrings, which means sliding window is actually solving a particular kind of problem for subarrays and substring which does not exist for the subsequence. And what this problem is, we are going to discuss in one of the next sections in this video. The next question is, where do you really use it? So you use it in linear data structures like array, strings and linked list, which means you do not use it on this kind of structure like a tree or a graph. You will usually do not use sliding window in this kind of structure. Why? Because it is hard to get access of contiguous elements without doing some calculation. So if you are in a graph on this node and you have access to this node somehow, then in order to get access to this node or this particular node or this particular node, you will have to do some calculations, right? You will have to go there, you will have to figure things out, because it's not easy to get access of multiple elements in a graph in constant time. And that is why even if you try to use sliding window in these kind of graph problems or some other data structure problems, that will not be optimized. That will actually be an overhead. That's why we only use sliding window in arrays, strings and linked list. Why? Because we are dealing with a window of data that moves sequentially across structure, maintaining a contiguous block of elements. And since we are dealing with a contiguous block of elements, it becomes very important for us to get access to the elements in order of one time complexity. And this kind of access time complexity only exists for arrays, strings, or sometimes linked lists. So what it means is that if in your question you have to deal with the contiguous range of elements and you have been given an array, string, or linked list, then there is a high chance that you can actually go ahead and use sliding window, because sliding window works on these two things: the linear data structures like array, string, and linked list, and the contiguous range of elements. Now the next question is, why do you use it? There are mainly two reasons to use the sliding window technique. First of all, if you have a solution like order of n square or order of n multiplied by k, then it means you are using nested loop somehow, where you are repeatedly, note the word repeatedly, calculating the data over overlapping ranges. Do you understand? We will have overlapping ranges and we will be doing something with those ranges. And because of these overlapping ranges, we will have nested loops returning us order of n square or order of n into k complexities. And this is the kind of situation where we can use the sliding window to reduce the time complexity to order of n. How does this actually work? We are going to see in the next section in the video. Don't worry about it. Then the second point is that we want to avoid recalculating the middle part of a particular range. Okay, so middle part is important. It means we are just removing all the ending nodes or all the ending elements. So instead of recalculating the whole sum or count or anything that we were trying to do with the elements, when moving to the next position or next range, we can simply update the changes, simply add the new element, remove the old element. We will see how it works in the next section. Don't worry about it. So after understanding everything till now, we can make a few conclusions. We can use sliding window technique whenever we are dealing with continuous or contiguous range of elements. Then we will need linear data structures like arrays, strings, and linked lists. Then if we see that the brute force solution actually takes order of n square, or it takes order of n multiplied by k, where k is a constant, or some other variable where k is another input, then we can think of using sliding window technique to optimize these time complexities to order of n. And so what this means is that in the question you will have to see if you're dealing with continuous ranges, if you have linear data structures, if you have this kind of time complexity in the brute force solution, then you can make a very good guess that okay, you can use sliding window technique. Because guys, sliding window technique is not a one solution that fits everything. It is a technique that is used in specific situations. And these points are basically the indication that you are in that situation where you need to use sliding window. So do not try to understand this point in isolation, because all these points are working together to make sure that the sliding window technique or the sliding window solution will actually work in that particular problem. So make sure to read the problem properly so that you will have all the points that you need to understand whether you should use sliding window in the problem or not. Now the next question is how? How do we have an order of n square solution and we can convert it into the order of n? Because it is one of the most important things to understand, because if you understand why this happens, you will be able to understand whether you can use sliding window in a particular solution or not. Understanding this is like the holy grail of sliding window. You will never have any issues with the sliding window ever in the future. So to understand why this happens, we need to understand what kind of problem we are trying to solve with the help of sliding window technique. So usually you will have an array or a string where you will have a few elements. Here we have 1, 2, 3, -1, -1, and 5. And then the question will ask us to do something with the sub-arrays or substrings. Since we have an array, so we are going to do something with the sub-arrays. Suppose that the question asks us to find a sub-array that have the maximum sum. We need to return its length. So what can we do to find the sub-array with the maximum sum in this given array? Well, we can try to use brute force to find all the sub-arrays and then calculate the sum of each and every subarray and then check which subarray had the maximum sum and then simply return the length of that subarray. And when we are doing that, we will be doing something like this. We will have a for loop that will run from I is equals to 0 to the end of the array. So right now we have indices 0, 1, 2, 3, 4, 5. The length of the array is 6. So it will run from 0 to 6. Then we will have another for loop that will run from j is equals to I till end, that is the 6, length of 6. Then we can have another for loop where we will run from I to j, and this is basically the subarray. This for loop, the I to j, is basically the subarray that we found, and then here we will calculate the sum. We will calculate the sum of all the elements from I to j and then we can just check if it is the maximum sum or not. If it is not the maximum sum, we just keep on going. Okay, in this way we are going to find all the subarrays and then calculate the sum of the subarrays and then just return the length of the subarray that have the maximum sum. But as you can see that we have three loops right here. This particular for loop is actually used to calculate the sum of the array. So this for loop is not really a part of finding the subarray. It is just taking all the elements in the subarray from I to j and calculating the sum. That's why only these two for loops are actually part of finding the subarray, the starting and the ending index of the subarray. So I represent the starting index and j will represent the ending index of the subarray. And so this part is going to take order of n square time complexity. You can understand it in two ways. First of all, we have these two for loops that are nested within each other. So they will end up with the order of n square time complexity because they are going through the entire array, right? The other way to understand this time complexity is to understand that there are n square subarrays for any given array. And since we are going through each and every subarray, we will have to run the loop for n square time. And that's what is coming here. So that's how we get this order of n square time complexity. Now, how do we reduce it to order of n? That is the biggest question. Now, one thing to note is that we have I and j, we have two pointers that we are using to actually calculate the sum of the entire subarray. So what we can say is that we can use two pointers to represent a subarray, right? I can place a pointer p1 right here, and then I can place a pointer q right here, and then I can say that, okay, every element from p to q is part of a subarray, right? So I can simply use two pointers to represent any subarray that I want, right? Can I represent every subarray with these two pointers? Yes, I can. Can I go through all of them? Yes, I can. But if I go through all of them, then this n square time complexity will still be there. So we can try to remove the for loops with the help of pointers somehow. But how do we remove the n square time complexity, right? And a promising way to do that is by reducing the number of subarrays that we go through. So for any given array, we can have a lot of subarrays. We can have a single element subarray. We can have two element subarray like 1, 2. We can have three element subarrays like 1, 2, 3. We can have four element subarray 1, 2, 3, -1, right? We can have arrays like 2, 3, right? We can have arrays like 3, -1, right? We will have lots of subarrays for this particular array that I cannot even write them right here. And because there are so many subarrays, and if we try to go through all of them, we are reaching the order of n square time complexity. So if we somehow reduce the number of subarrays that we have to go through in the question, then we will be able to reduce it to order of n. Now the way we reduce the number of subarrays that we have to go through depends on the condition of the question. So the question will always have some condition that will help you to determine how to move these p and q pointer so that you will not have to go through each and every subarray that can be made with the given array. And we are going to use examples to see what those conditions can be. But understand that the reason we can go from order of n square to order of n is because the question itself will have some conditions that will help you to skip a lot of these subarrays which are not going to give us answer in any way. For example, right now we are trying to get a subarray with the maximum sum, right? So I need to maximize the sum. It means if I try to add 3 and -1, it is going to give me 2, right? Which is less sum. So it means I need to have a way to skip 3 and -1, this particular subarray. And just like this, there will be many subarrays that will simply not help you to go to the answer anyways. There will be some subarrays that can have potential answers. So the conditions in the question will help you to go through those subarrays only, but all the other subarrays will simply be ignored automatically. You will not have to skip them manually. They will simply be skipped automatically if you use the conditions in the question smartly. And all this discussion is also valid for substring. So we can have string like A, B, C, D, E, right? The indices will be 0, 1, 2, 3, and 4. So the entire discussion that we had till now is also valid for strings and substrings. Now there are two types of sliding window technique. The first one is the fixed size window. The distance between the pointers is constant, and the other one is dynamic or variable size window, which basically means the window will expand and contract or shrink based on the conditions. Now these conditions will be given in the question itself. So in the first situation, you will have an array or a substring and you will have p and q at a certain length. So right now the length is 4 elements, right? This length will not change. It means if the q is shifted to here, the p will also be shifting to this side, maintaining the same distance again, which basically means that we have a fixed window or fixed number of elements between the p and q, and that's why it is called fixed size. This kind of thing happens when we are trying to do calculation on the subarray or substring of a fixed length. For example, you want to find out the substrings or subarrays of size 4 that have the maximum value. What this means is that we will go through the entire array with P and Q at a distance of 4, and we will keep on shifting this P and Q with the distance of 4, calculating the sum of elements between P and Q. And whenever we find the maximum sum, we can simply store it and later on return it. Now in the dynamic type of sliding window technique, we have a few things to notice. First of all, these P and Q pointers does not need to maintain a fixed length between them. So if I decide to shift Q to here, I don't need to shift P. Okay, I can simply increase or decrease the length between P and Q. What this means is that we can effectively increase or decrease the size of the window of elements. But then again, guys, if we can increase and decrease the size of the window however we want, then how can we ever achieve a result? How can we ever decide that, okay, now I want to increase the P, right? So it means that the increase and the decrease in the size of this window is going to depend on something. Okay, and that something is the conditions in the question. So the conditions in the question will help you to understand when to increase and decrease the P and Q pointers. Basically, you will have to figure out a valid window. Okay, not every window is going to be valid. So while the window is valid, you can keep on increasing the Q. Okay, and when the window is no longer valid, you can increase the P to make the window valid again. And now, what is the condition for a window to be valid? Those conditions will be provided in the question itself. So you will have to really look at the question, understand it very well to understand what exactly is a valid window. For example, a window can be valid if the sum of the elements in the window is positive. So if I write something like negative 500 here and the Q is not here, Q is right here, okay? So P is here, Q is here. The sum of the elements here is what? 4 plus 3, 7, 7, 8, 9, 10, right? It's a positive sum right now. But if I shift the Q to the next element, that is negative 500, then the sum will be what? Well, negative 500 plus 10 will be negative 490, right? And now the sum is what? It is negative, right? So our condition was the sum should not be negative in the window. And now that we have the sum negative, we can start incrementing P, okay, till we reach Q. And if we reach Q, we will just end up incrementing Q and P again to the next index. So these kind of conditions will be present in the question that you will have to look for, and they will decide what is going to be conditions for a window to be valid. And while the window is valid, you can keep on increasing the size of the window. And when it is no longer valid, you can simply increase the P pointer and decrease the size of the window. So this is really important. The condition that will make the particular window valid, you really have to look out for these conditions in the question and make sure you understand it very well. Suppose we have an array of integers and a number k. Find the maximum sum of any contiguous subarray of size k. Great. We have a linear data structure here, right? We have integers here. We have a number k that is input, and we have been explicitly told that we need a contiguous subarray of size k. Okay, so these are a lot of indication that tells us within the question itself that we can try to go ahead and use sliding window. And if we look at the brute force solution, the brute force solution of this problem will be what? It will be to find all the subarrays of a given array, and then out of them the subarray of the size k, we have to take them and we have to calculate their sum, and then we have to return the greatest sum. And this is going to take at least order of n square. If you include the time for actually calculating the sum, then it will become order of n cube. So the time complexities of the brute force solution also aligns and actually indicates us to go ahead and use sliding window technique. So suppose that this is the array that we have and the k is 3. It means we need to find out all the subarrays of size 3 and we have to calculate their sum and we have to return the maximum sum. So how can we do that? Well, we can start with having two pointers. We will have P here and Q here, okay? And right now the size of the subarray is what? It is 1 because there is only one element in the P and Q distance. So it means the maximum sum is simply 1 right now. Now what we can do is we can increase the Q. So the Q will go to the next element that is here. And now what is the maximum sum? Well, we can simply add 2 in the original max sum instead of taking 1 and 2 again and calculating their sum in a different loop, right? Because we already have a result from the previous subarray. So I can take 2 and add in the 1. So it will become 3, right? So it means the sum till here is 3. The size is not k. The size is what? The size is 2 elements right now. So it means it is not an answer. Now we will shift the Q to the next element. And then we have what? We have 3 here. Now in order to find the sum of 3, 2 and 1, what we can do is we can simply add 3 here, right? Because we already have this 3, the sum of previous 2 elements, and so we can simply add the next element in the sum and we will get 6. It means the sum of this entire subarray is 6. Do you notice how we are using the previously calculated sum to calculate the sum for the next subarray in a constant time complexity, just because we are taking the next element and adding it in the max element that we already have. And this reuse of the already calculated value is also one of the reasons to use sliding window technique. So now we have 6 here, okay? Now we have the length 3. So the P and Q are at a distance 3. 3 is basically what? It is equal to K, right? We must not go above K because we just need subarrays of length K, right? So this is a fixed sliding window technique. The reason we started with Q on the first place is just to make sure that we reach this length 3, and then we can just keep on shifting P and Q together. So now that I want to shift the Q again, I will take the Q from here, I will shift it here, Q will come here, then I will again take the P here and then shift it to the next index, right? And then P will be here. But now as you can see that I shifted the P from 1 to 2. It means in the current subarray. So current subarray is what? This 2, 3 and 4. What this means is that in the current subarray, we don't have 1, right? It means we should remove 1 from this maximum. So it will become 5, okay? And then since we are actually adding 4 in the subarray, we should also add 4 here to calculate the sum of this particular 2, 3 and 4 subarray. So 5 plus 4 is equal to 9. So it means the sum of this particular subarray is 9. Now do you understand how we are able to update the maximum sum just by shifting P to the next element and Q to the next element? If we shift the P to the next element, we remove the previous element from the max, and if we shift Q to the next element, we add this particular next element into the max. Simple, right? We don't have to take the entire subarray 2, 3 and 4 and use a loop to calculate their sum again. And so max till now is 9, right? Now if we try to move ahead, if we try to move the Q here, we cannot do that because we no longer have any more elements. So we cannot do that. We can simply end the loop and return the 9 as answer. Now one more thing that you should notice is that we never calculated for 1, 2, 3 and 4, this subarray, right? We never calculated the sum for this subarray. We skipped it. Do you understand it? We skipped this subarray. In the same way, we never calculated the sum for 3, 4 subarray. We skipped it, right? We never calculated the sum for 2, 3 subarray. We skipped it, right? All these arrays and many more arrays actually got skipped automatically just because we were following the rules of given in the question. So it means the conditions in the question will help us to skip all these unnecessary subarrays automatically. And here you can see that we only have P and Q pointers, and those pointers are going to reach each and every element only twice. So what this means is that Q at max can cover n distance and P at max can cover n distance, right? So it means P and Q together will cover n plus n distance, which is going to be 2n, which is simply going to be order of n. Why? Because we will simply remove the constant. We don't need constant in bigger time complexities. And what it means is that we went from the order of n square time complexity in the brute force to order of n in the sliding window approach. Now here is another example. We have been given a string and we have to find the length of the longest substring without repeating characters. So basically we have a linear data structure string. We have to find the length, that is something we have to find, and we have to do it for a longest substring. We have a substring here, right? And we have this condition without repeating characters. So we have a condition, right, from here to here. So all these are very good indication that we need to use sliding window technique. And the brute force solution for this problem can be finding all of the substrings that are possible from a given string, and then separating out all the strings that do not have any repeating characters, and then just returning the maximum length out of them. That can take around order of n cube time complexity, which is a very good indication that we should use sliding window technique. Now suppose that we have a string like this, and since we have to make sure that we do not have repeating characters, we need some kind of place where we can store whether we have actually encountered a particular character or not. So we can store that in a set. We will have a set like this, and inside of it we can store the character that we have encountered till now. And the set does not contain duplicates. It means if I add D 2 times, so I add D here and then I add D again here, I will only have a single D character in this set, which is a good thing for space optimization. So now we can try to go ahead and solve this question. We will have a P here and a Q here. Okay. Now since we are on the A here, I will take this A and I will first of all check, is this already present in the set? It is not in the set, right? So I will take the A and place it inside of the set here. And A itself is a substring right now, and it does not have any repeating character, so it's a valid substring. So what I will do is I will simply take the Q and shift it to the next index, that is B. So what this means is that in this question, the conditions for making sure that a particular window is valid is to make sure that there are no repeating character in the window. So I have the Q here. Okay, I will check if B is already present in the set. It is not present, right? So I will take the B, I will place it in the set. Then I will again move to the C. So Q is here, it is no longer here. I will check if the C is present in the set. If it is not present in the set, I will add it in the set. Then I will shift the Q to the next character, that is D. Now I will check if D present in the set. It is not present in the set, so I will add D here. Then again I will shift here and I have a D again. So I will check, is D present in the set? It is present in the set. It means the window, this particular window from A to D is not valid, because what it means is that this particular window does not have unique characters. It have some repeating characters, and that's why it is not valid. And now what can we do to make this valid? Well, first of all, we only know that we have D, this character, somewhere in the string. Okay, we don't know whether it is right here or in the beginning. We don't know that, right? So what this means is that we will keep on shifting P until we make sure that D does not exist in the string. So what we can do is, we will take the character at P, that is A, and remove it from the set. It is no longer in the set. We will shift the P again. P will be here. We will check if the character at Q still exists in the set. It does. D still exists in the set. It means we need to take the P and we need to shift it again, right? So before we shift it, we will take the B and we will remove it from the set, because B is no longer in the window, right? So now we shift the P to the next one. Then we take the Q and we check, is D still present in the set? It is still present in the set. So we will shift the P again here and we will take the C, we will remove it from the set. Now we will check again. So is D present in the set? It is still present in the set, right? Then we will take the P and we will have to shift it again. So here it will be P, and before shifting we will just take the D and remove it from the set. So now D does not exist in the set, right? And now when we take the Q and we will check if D exists in the set, it does not. So we will simply take this D and place it inside of this set. So D will be here. Simple as that, right? And then we will simply shift the Q to the next element, that is E. Is E present in the set? It does not exist. So we will simply add it. And if we try to shift it again, it cannot be done because there is no other element or there is no other character. So it means we can simply stop the loop. And now remember that we had to return the length of the longest substring, right? So we will have a result variable that will be equal to 0 in the starting. And as we kept on increasing the Q, while the window was valid, we will keep on incrementing the result variable also. So when P and Q were in the starting position, we will simply add 1 here. Then as Q shifted to next position, we will keep on adding 1. Okay. Then as it again shifted, we will keep on adding 1. Then it shifted to the D, we will keep on adding 1. Then it shifted to this D, right? Here. And this is where we actually started incrementing P, that is removing these elements from the set. So we will not increment right now. And as P reached this particular element after removing all these from the set, we will see that is the current length of the window greater than the result? Well, right now the result is what? 1 plus 1 plus 1 plus 1. It is equal to 4, right? So current length of window is 1. It is not greater than 4. So we will not really add anything. We will not update it, right? Then we will again shift the Q here and we will see it is on here. The current length is what? 2. It is not greater than 4. We will not update it. We will only update this thing when the length of this particular window is going to be greater than the result. So the length of the window can be calculated like this: Q minus P plus 1. This is going to be the length of the window. And if it is greater than the res, we will simply say res or result is equals to Q minus P plus 1. This is going to be the condition that will update the result variable. And at the end of the day, whatever is going to be the maximum value in the result, we will simply return that as answer. And here also you should notice something, right? We never ended up going through the string B and C. This was also a substring, right? But we never really went for it. We checked for A, we checked for A, B, we checked for A, B, C, okay? We checked for A, B, C, D, but we never really checked for BC explicitly, right? What this means is that I ended up skipping this particular substring. In the same way, I skipped C, D also. I skipped this. I also skipped the string B, C, D, right? Because A, B, C, D is not same as B, C, D. So these are different substring. So I ended up skipping a lot of substring just by following the rules given in the question. And that's how I was able to go from order of n square to order of n. Why? Because these P and Q pointer are again going to go through the entire string, right? So if P is traversing the entire array, it can only traverse till n at max. If Q is traversing the entire array, it can also traverse only n elements at max. What this means is that time complexity is going to be n plus n, right? It is going to be 2n. So big O of time complexity of 2n is going to be order of n. Simple, right? And that's how we achieved this particular result. Now here is another example. Suppose we have an array of positive integers and a target number. We have to find the minimal length of a subarray whose sum is greater than or equal to the target number. So here we have a linear data structure array and we also have a subarray. Subarray represent the contiguous range of elements. So basically we have two things that are actually indicating that we can use sliding window technique. And then we also have this condition, sum is greater than or equal to the target. So this condition will help us to actually skip many of the subarrays. And also the brute force way to solve this question would be to find all of the subarrays, then find all the subarrays that actually have a sum greater than the target, and out of them we have to find a subarray that have the minimum length and we have to return that minimum length. And that is going to take order of n square time complexity just to find all of the subarrays. And so with all these indications, it is very clear that we are supposed to use sliding window technique in this question. So suppose that we have this particular array and then we have the target to be 10. So we need to find the subarray that have the sum equal to or greater than 10 and have the minimum length. So what we can do is we can start with the p and q at the first element and we check, is this going to be greater than 10? It is not greater than 10, right? So it means I need to increase the q to next element. So q will be here. So what this means is that the conditions to make the window valid is that the sum of the elements in the window needs to be greater than or equal to 10. So with that in mind, now let us try to calculate the sum for this particular window. So we already had 2 here, right? So it means the current sum was already 2 earlier. I just forgot to update it. Now that we have 9 here, I will simply add 9 here, okay? So it gives us 11. It means we have a valid condition here. It is greater than 10. So I'm going to take the length of this particular window. The length is going to be q minus p plus 1, okay? Which is going to be 1 minus 0 plus 1, which is going to be 2, right? So I will check which one is smaller. Is this smaller or the minimum length that we already stored is smaller? So this represents the infinity. There are different ways to represent infinity in different languages. So here it is very clear that this is greater than this, right? And I need the minimum. So I will take the 2 and I will replace infinity with 2. So till now the subarray that have the sum greater than or equal to 10 have a length of 2. And so now what should we do? Should we shift the q or should we shift the p? We should shift the p. Why? Because we need to get the minimum length. If I try to shift the q, I will reach here. It means I will have a length of 3, right? It will become greater than 2. But I need something less than 2, right? So what I should do is instead of increasing the q, I should now increase the p. Why? Because we already have a valid window, right? So I need to figure out, is there a valid window smaller than current one? So I will increase the p, then the p will be here, and once I shift the p, I will take the 2 and I will remove it from the current sum. So it will become 9, right? And right now the current sum 9 is less than 10, which means it is not a valid window, okay? And at this point, I'm going to shift the q again to get another valid window. So q will be here, right? And as I shift the q, I will take the 1 and add in the current max. So it will become 10. Now it is 10. So it is basically equal to 10, and that means this particular window is basically a valid window. So I will check what is the length of this window. It is 2, right? So I will not be able to replace 2 with 2 anyways. So I will again try to find a valid window of a lesser length. So I will again shift the p. So p will be here and I will remove 9 from this 10. So the current sum is 10 right now. I will remove 9. It will become 1. And 1 is not greater than or equal to 10. So it is not a valid window. So it means I will again shift the q to the next element. We will have here. And right now we will simply add 3 in the current sum. It will give us 4. 4 is also not greater than or equal to 10. So I will simply take this q. I will shift it again. I will reach 500. Then I will add 500 to 4. So it will make 504. So 504 is definitely greater than or equal to 10. So I know that I have found a valid window, right? So p is here and the q is at the ending index. What is the size of it? It is 3, right? There are 3 elements, 1, 2, 3. So the size of the window is 3. But the minimum size that I already stored is 2. So 3 is greater than 2 and I need to store the minimum length. So I will not store 3 here. I will let it be 2. So now that I have a valid window here, I will try to find a valid window that is smaller than this. So I will keep on shifting p now. So p will come here, right? P is no longer here. So I will take the 1 and I will subtract from 504. It will become 503. It is still valid, right? And the new window is 3 and 500. That is the length of 2. So there is nothing to update because they are the same, right? Then I will again try to find another valid window by shifting p. So p will be here and right now the window is just 500. So basically as I shifted p, I will remove 3 and it will become 500 again. So 500 is definitely greater than or equal to 10. So I will try to calculate the length of the window. It is 1, which is less than 2, right? So it means I will end up replacing 2 with 1. So here will be 1, and 1 will actually become the answer because there is nowhere else to go after this. No element where we can shift P and Q. So 1 will be the answer and we will return that. So as you can see here that whether a particular window is valid or not depends heavily on the question itself. You really have to look at the question and understand it very well to understand how you are going to move P and Q and when you are going to move P and Q. That is a really important step. And here in this question also you can see that we never went for 2913, this subarray, right? We never went for this. Why? Because we never needed to. We actually just skipped this, right? We never calculated anything for this. We never went for 2, 9 and 1 also, right? This subarray was also skipped. So in this way, many other subarrays were actually skipped automatically just because we were following the rules from the question. And that is why we were able to take the order of n squared solution to order of n, because here also we have P and Q, right? So P can only move till n elements, Q can also move till n elements. So we will have n plus n, that is 2n. So P and Q together moved to n elements, and that means we will simply have order of 2n time complexity, which is basically equal to order of n time complexity. And that's how we are able to get this result. So yeah, if you find this video helpful, then just like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.